Okay. Yeah, welcome back to the final lecture on tropical geometry. Let me start by summing up what happened last time. We introduced numbers in algebraic geometry, which are called NDG, and which are a count of algebraic plane curves, degree D and genus G passing through 3D G minus 1 points in general position. We looked at a few examples. The most basic example, of course, is going to be N10, which is just the number of lines through 2 points, where we all know that's 1. And on the tropical side, we convinced ourselves that 3D plus G minus 1 points is indeed the right number of points to obtain something 0-dimensional, something finite, not like a higher dimensional family of curves satisfying those conditions, but really something finite. Then on the tropical side, we studied the analogues of degree and genus. And for the degree, it was the number of n's in the 3 special directions. And then we viewed tropical plane curves as being parameterized by an abstract graph. An abstract tropical curve, I should say, which is a metric graph. And then the genus is the genus of the graph. And let me draw an example. So what we have to pay attention to in particular is that there may be crossings of edges. Crossings of edges in the dual world correspond to a parallelogram. So I can draw a picture of a cubic for you with one parallelogram, for example, like this. And then the dual tropical curve would look as follows. And this is an example of a rational tropical cubic. And again, it is rational because this is not viewed to be a vertex, but a crossing of 2 edges. So we parameterize this by an abstract graph, which is a tree, which does not have any genus, and which sort of looks like this. And those 2 edges then cross in the image. Okay, and then as I also said, we discussed the dimension of the moduli space of tropical curves, and we convinced ourselves that we can fix, well, no, sorry, let me put it differently. If we fix, 3D plus G minus 1 points and study tropical curves of degree D and genus G passing through those points, then we expect a finite number. Yeah, and that's for dimension reasons, because we convinced ourselves that the dimension of the moduli space of tropical curves is 3D plus G minus 1. Okay, so with that, we're pretty close to defining the analog of the number above in the tropical world, which will be called NDG trop. And it should be something like the analogous count of tropical curves, but I'm not quite yet ready to define it. I have to introduce two more concepts. So let's move on. The first concept is the definition of a simple tropical curve. And a tropical curve is called simple. So let's discuss abstract curves, sorry, parameterized tropical curves, gamma, phi, such that phi of gamma is an embedded plane tropical curve, these objects that we started the course with. Such a parameterized tropical curve is called simple if, if the abstract graph is three-valent and the image phi of gamma in R2 is dual to a subdivision that contains only triangles and parallelograms. And how are you supposed to understand that? Well, the triangles are dual to three-valent vertices, and the parallelograms are dual to crossings, right? So we have a triangle, it's dual to a three-valent vertex of my curve. We have a parallelogram, it's dual to what we want to think of as a crossing, because we're parameterizing our tropical curve. And I think that then it's clear why we're making this definition, because last time when we discussed the moduli space of tropical curves, we convinced ourselves that the highest dimension you obtain for three-valent tropical curves, because as soon as you have a higher valent vertex, we've drawn one example for such a higher valent vertex, maybe something like this. As soon as you have such a higher valent vertex, you can resolve it, not only in one way, in several ways, right? And then you gain a parameter of freedom, you gain a new length for a new edge, right? And so you grow in dimension. So being three-valent will bring you to the top dimensional cells of your moduli space. And that's also the reason behind the following fact. If we fix 3D plus G minus 1 generic points, only simple tropical curves of degree D and genus G pass through them. And let me repeat the reason for why this is true. The reason is that we have a map from the moduli space of tropical curves, which evaluates the points, so to say, which checks which points you pass through. Map from moduli space of tropical curves to the space of point conditions and you can show that this is locally a linear map and non-simple tropical curves are of lower dimension in the moduli space. But then also the images of these sets of non-simple tropical curves in the space of point conditions will be of lower dimension. And so if we just avoid those lower dimensional space, if we pick generic points, we never get those. For generic points, we'll always only get simple tropical curves. An example for a simple tropical curve was on the slide, just one slide before. This tropical cubic, this rational tropical cubic that we've drawn was a cubic that had in the dual subdivision only triangles and parallelograms. So that was a perfect tropical, simple tropical curve. And now the final concept before we can introduce the tropical count is the multiplicity. It turns out that you have to count tropical curves with a certain multiplicity. The reason is the motivation. It comes from the motivation. We know that algebraic curves degenerate to tropical curves. Well, it's not only a motivation for us right now because we studied this. We studied algebraic curves over the Puiseux series. We used -val to degenerate. We obtained tropical curves, right? And now if you count algebraic curves, so assume you have a finite set of algebraic curves through some fixed points, right? That satisfy point conditions. You degenerate them, you also obtain a finite set of tropical curves, But this map, so to say, is not of one-to-one. It sends possibly multiple algebraic curves to just one tropical curve. So let me just sketch something. Here's my finite set of algebraic curves. Here's my finite set of tropical curves. And possibly multiple algebraic curves go to one and the same tropical curve. Yeah, like in my sketch now, I have to count the first one with multiplicity 3 and the others with multiplicity 1 in order to reflect the count in the algebraic world. So this is why we have to count with multiplicity. But the good news is that you can compute this multiplicity on the tropical side purely combinatorially. You don't need to know much about the algebraic curves from which your tropical curve comes, which degenerate to your tropical curve. And that's good that you don't need to know that because that's rather difficult to figure out. But as I say, there's really only a combinatorial recipe. And this recipe is as follows. So let's start with the vertex. We assume we have a 3-valent vertex. And then we let T be the dual triangle in the dual Newton subdivision. And then we define the multiplicity of V to be the normalized area of T. And we define the multiplicity of a tropical plane curve, the product over all 3-valent vertices of a simple tropical curve, I should say. Because then we have only 3-valent vertices, and we take the product of the multiplicities. So let me give you an example of this. And let me also explain what I mean with this normalized area. It's like a lattice area. So here's an example. Okay, so this is a cubic. And it's a rational cubic because it's parameterized by a tree. It has one edge of weight 2 because you see here is an edge of lattice length 2. Okay, and then we have a bunch of vertices. and we can see the dual triangles for the vertices. And such a triangle is viewed to be of area 1. The area of this triangle, the normalized area of this triangle is 1. It's viewed to, it's like a lattice area. So you take the smallest simplex that you can draw in this lattice, and this would be one of the smallest simplices you can draw in this lattice, and then this has area 1. So you may be used to calling the area of such a triangle 1/2. Yeah, so the Euclidean area would be 1/2, but we normalize the lattice area. So you can also, this normalized, you can just view as times 2. Times 2, usual Euclidean area times 2. Okay, and now maybe I can ask you, what is the area of this triangle? I think I heard it already, 2. Very good. And analogously, this also has 2. All the others have area 1 though. And so what is the multiplicity of this tropical curve? That's 2 times 2 times 1 times 1 times 1 times 1 times 1, and that's 4. Okay. Let's do one more example. Let's draw another rational tropical cubic. Also has only, it's simple, it has only triangles in the subdivision right now. So let's draw the tropical cubic. And it looks like this. And you all see immediately it has tons of area 1 triangles again. And then it has one special triangle. And what do you think is the area of this one? Yeah, I think I heard it again. It's 3, right? Because you can sort of subdivide into 3 smallest triangles. So it's 3 times all ones. So that's a tropical curve of multiplicity 3. Okay, great. So now we are ready to define this number NDG trop, which I promised. So that's the number of tropical plane curves of degree D and genus G through 3D plus G minus 1 points in general position, counted with multiplicity. Okay, and now comes the magic theory, a very famous theory in tropical geometry. Oopsie, the correspondence theory by Michalkin. And it states, as you can guess, that this number NDG equals the number NDG trop. And why is this theorem so great? Because it now gives us a way to, on the tropical side, count our piecewise linear graphs in the plane somehow. And with that, we obtain, in the same way, a count of algebraic curves, which was a very complicated question for centuries. People didn't know how to compute this number for centuries. Then also there were some recursive formulas, but nevertheless, now we have a new tool to approach these numbers in the algebraic world by means of tropical curves, by means of tropical geometry. And this also helps to find out new insights about those counts of algebraic curves. There are also new numbers that have been produced using tropical geometry. But what we still have to do in order to feel like we seriously achieved something is that we have to find a way to actually count those tropical curves. This is something that we discussed a little bit at the end of the lecture yesterday already. If I give you 2 points and ask you to draw the tropical line through those, you won't have any problem for sure. But if I give you 5 points and ask you to draw the tropical conic through those, or if I give you 8 points and ask you to draw the tropical rational cubics through those, you don't really know what to do. I mean, you can try to start somehow, but it's really terrible, right? So we need something better. We need like an algorithm to compute the number of tropical curves, because once we can really compute on the tropical side, we can use the tropical side to get new insights about the algebraic sides, and that's what we aim for. That's what we want to do. Okay, and what do we do for that? We pick points in general position, but in a special general position, so to say. We pick a small strip, small horizontal strip, so to say, and then we spread our points in this strip, and they are very far away from each other. But they still need to be in general positions, so they are not allowed to be on a horizontal line also, just very far from each other, but in this strip, okay? And what happens when you draw tropical curves through such point conditions? Let me actually cheat a little, because it's very hard to draw the points first and the curve next. Let me start by drawing a tropical curve. And admittedly, it's also very hard to draw that many points in such a position, but I'm trying. Okay. So I'm going to draw the first 3 points not so extremely far apart, but you can imagine, let me actually do it like this. You can imagine that those edges here continue for very long, and that this point is just coming very much to the left, okay? Far left here. And also far apart from each other, the points, okay? It's just that my screen is too small to really seriously draw this. Okay, and the next points, they're all, so if we view this as stretched very far left apart, then all those points are in a small strip, but far from each other. And you can prove that if you choose a point condition like that, what will happen is that your tropical curve gets floor decomposed. So this is another fact. Tropical curves through, now let me actually give this a name. These we usually call horizontally stretched point conditions. Horizontally stretched point conditions. And tropical curves through horizontally stretched point conditions are what we call floor decomposed. And floor decomposed means in the dual subdivision, all vertical segments are there. So what do I mean by this? I mean, all those edges have to be there in the subdivision. So when we compare with the tropical curve we've just drawn up there, then we can look at the dual Newton subdivision. This is floor decomposed. That's no surprise, because it does go through such vertical, it's just horizontally stretched points. Let me also show you an example of a subdivision which is not floor decomposed. Oops, sorry, that was too much. this subdivision that we also looked at earlier, this is not floor decomposed because this is not part of the subdivision, right? Not floor decomposed. Okay, and what's the reason for this fact? The reason is that the points are sort of so far apart from each other that you need to have a horizontal edge connecting, going through a point before you meet another point. Somehow you do need to have those horizontal edges, and horizontal edges are dual to the vertical segments in the Newton subdivision. That's the reason somehow behind this fact. So what do we gain from having such floor decomposed tropical curves? What we gain is that we can sort of distill the combinatorial essence of the tropical curve count by doing the following. Now, I should also say a word about the terminology. So the terminology is coming from the following. So we call those horizontal edges, we call those elevators. And then what we do is we take such a component, take a component of the tropical curve minus the elevators. That will be a path connecting a downwards end with a diagonal end. And these things are called the floors. Floors. And now the terminology makes some sense if you turn the picture around. And some people do that. It's just a convention yet again. Yeah. Then we have floors and elevators like in a skyscraper, right? Now, so, okay, we sort of put our skyscraper lying down on the floor for this moment, right? That's the terminology. Okay, what do? We sort of take a floor and shrink it to just a point. And by doing that, we produce a linear graph, a graph on a linear point set from our floor decomposed tropical curve. And these graphs are going to be finite objects that we then can count very easily. I'll show you. So first, let me sketch this so-called floor diagram that we produce from the tropical curve. I will define it in a second, but let me just to give an idea first of what is happening. Let me sketch this floor diagram before having defined it. So we take a linearly ordered set of points, and these are sort of the projections of our point conditions. Well, we want our points to have two colors, depending on whether they are elevator points or floor points. And let me draw the floor points with an additional yellow right now. And then we just keep the elevator edges. And we sketch how they connect. Yeah, I'm not drawing them as straight lines right now because after the projection, they will all lie on top of each other and you can't see it. And we just sketch how they are. Oh, sorry, this is of course an edge of weight 2, and the weight is preserved. The weight is preserved. Okay, so this would be the floor diagram we obtain from this tropical curve above by sort of just projecting the floors away. Okay, now let's take a fresh screen and let's really define what a floor diagram is. Floor diagram. Floor diagram is a graph on a linearly ordered vertex set with vertices colored black and, well, I used yellow before, but standard is black and white, and edges equipped with weights such that the following conditions hold. There are d wide vertices and 2d plus g minus 1 Plaque vertices. The definition continues, but before we do that, let me tell you that I want you to think of this definition as those devices which are produced from floor decomposed tropical plane curves passing through horizontally stretched point conditions. And if we view those floor diagrams like that already now, we can explain to ourselves why this definition is made the way it is. So for example, we know already we have this graph on a linearly ordered vertex set because this is just the order of the point conditions, the horizontal order of the point conditions. We know that we want Plaque and wide vertices because we have floor points and elevator points. We know that the edges have to be equipped with weights because the elevator edges, the horizontal edges of our tropical curves can have weights, as we saw in the previous example. We know that there are d wide vertices. Why do we know that? I claim we know that. Why? Because there are d floors, right? If we count tropical curves of degree d, we have this triangle of size d. And now, because it's floor decomposed, we know that all those vertical segments have to be there. And the floors correspond precisely to what is in between. But there are d of those. So there are d floors, and for that reason also d wide vertices. And then because in total we have 3d plus g minus 1 point conditions, and d point conditions sit on floors, the remaining 2d plus g minus 1 point conditions must sit on elevators, must be elevator points, and for that reason we have 2d plus g minus 1 Plaque vertices here. Okay. Furthermore, we have d unbounded edges of weight 1, each pointing to the left. Well, where do those come from? They come from the d left ends of our tropical curve, right? They remain, they are elevator ends, and those elevator ends have to remain in the floor diagram. Then each white vertex satisfies the sum, oops, sorry, the sum of the weights of the incoming edges equal the sum of the weights of the outgoing edges plus 1. Why is that? Let's give a reason for that also. A reason for that is that such a white vertex corresponds to such a strip in my Newton subdivision for my floor, right? The strip could be subdivided somehow. I don't know precisely how. Maybe like this, or who knows, right? And dual will be the floor and some adjacent elevators, right? Yeah, and the adjacent elevators have some weights corresponding to the lattice length of those edges here, whatever that weight really is, yeah? But you see that we have one more here, one more that comes in, then everybody that goes out again, yeah? And that's precisely this condition here. Okay. Each Plaque vertex is of valence 2. And the weight of the incoming equals the weight of the outgoing. And why is that? Because the Plaque vertex is just like a point on an elevator. And if that edge has a certain weight, it has this weight on the right and on the left of the point, right? And the final part of the definition is the graph is bipartite. So that means it connects a white vertex with a Plaque vertex and a Plaque vertex with a white vertex, but never a white vertex with a white vertex or a Plaque vertex with a Plaque vertex. And what's the reason for that? The reason for that is that if you think of our floor decomposed tropical curve picture, let me try to sketch this quickly. Maybe I can make a rough sketch of the example we looked at before so that we can see that again. Yeah, just think of this as being horizontally stretched a lot. And these were the points. And then we had the corresponding floor diagram, which I want to sketch also. Let me sketch it here below. These are the D ends in my picture. D is 3, of course. Yeah, you see, it really is a bipartite graph. I'm only connecting yellow to white to black vertices and never black to black, never white to white. And the reason is that, so what would it mean if I had two white vertices which are connected by an edge? In my picture of the tropical curve, it would mean, so here's some floor, and here's some other floor, and there's an elevator edge that does not have a point on it, right? But if I had something like this, I could vary it. I could move the horizontal position of this elevator edge, and that's not possible because the tropical curves are fixed by the points. There's nothing that moves. We picked the number of points precisely to obtain something zero-dimensional, something that doesn't move anymore, right? So this is not okay. And what would it mean if we had an edge with two Plaque vertices like this? This would mean that we have an elevator in our tropical curve which comes with 2 points, right? Or at least 2 points. But that's nonsense also, because we asked our points to be in general position, and so there will never be 2 points on a horizontal line. So that's the reason for this being bipartite thing. So this is the definition of floor diagrams, and floor diagrams also have a multiplicity. Yeah, let me use a new slide. The multiplicity of a floor diagram is just the product of the weights of its edges. Now, in order to understand why this is the right idea, let me sketch one and the same picture again, because I think that picture is very helpful. This is a tropical curve we discussed before, and we also discussed the multiplicity of this tropical curve. Let me draw its dual Newton subdivision once more so that you have this and see this in front of you. So we discussed that this has multiplicity 4, and the 4 was coming from 2 big triangles, so to say. Almost all triangles had multiplicity 1, except for those 2, and those 2 have multiplicity 2. And why is that? Because they are triangles that have one edge of a higher lattice length, right? But now if we have floor decomposed tropical curves in general, what can happen? What triangles can we have? What's the possibilities for big triangles, so to say? Big meaning area bigger than 1. Well, that's only possible if we have like a big lattice length here. And the triangle sort of looks like that. And what is the area of a triangle like that? Well, it's going to be the same number as this lattice length here, yeah? And that lattice length, of course, is depicted in the weight of the edge. Yeah, so we have two vertices in this tropical curve. Sorry, I should add point conditions to my tropical curve. And I should also draw the floor diagram once more below it. So this is the floor diagram. This one elevator edge of our tropical curve gets cut into two edges of my floor diagram, right? And when we say the product of the weight of the edges, then here we obtain a 2 times 2, which is 4. So far that's good, right? But this 2 times 2 sort of is in charge of two vertices, this vertex and this vertex. And those two vertices are precisely the two vertices that correspond to those big triangles that we have in the dual Newton subdivision. So what I'm saying is, if I have an elevator in the tropical curve of a certain weight, then this elevator will end at two vertices. And those two vertices will be dual to, this is my weight. This is dual to my weight W elevator. Adjacent, I have two triangles that will be of area W, which is the same as the weight of my elevator. So this vertex has multiplicity W. This vertex has multiplicity W. This elevator will come with a point condition. So in the floor diagram picture, I will have a local picture that sort of looks like this. And I have two edges of weight W. And so this part of the tropical curve produces a factor of W squared to the multiplicity. And this part of the floor diagram also produces a factor of W squared to the multiplicity of a floor diagram. And for that reason, defining the multiplicity of a floor diagram like that does precisely the right thing. And we can continue and define a number which is the number NDG floor. And that's the number of floor diagrams of degree D and genus G, meaning through 3D plus G minus 1 points, right? The usual thing. Counted with multiplicity, of course. And then there's a theorem which states that this number equals the tropical number. And I think we are pretty sure already of why this is true, because there's actually a bijection between floor diagrams. So here are the floor diagrams that we count in our counting problem. And here are the tropical curves through horizontally stretched points. Yeah, let's pick such points. Through horizontally stretched points, I claim there's a bijection between those sets, and the bijection would then explain the equality. When I say bijection, it's to be precise, it's sort of a weighted bijection, because we count things on the right-hand side with multiplicity and we count things on the left-hand side also with multiplicity, but the multiplicity coincides and then the numbers coincide. So once we know this is a bijection, we are really all set. And why is this a bijection? I already told you how to get from a floor decomposed tropical curve to the floor diagram. All I need to do to make this a full proof is I need to show you how to go back from a floor diagram to a tropical curve satisfying the horizontally stretched point conditions, right? And let me sketch how that works. And let me try to do something like a proof by example again. So here are my horizontally stretched points. And again, let me choose to let the first 3 be not so far away for reasons of being able to draw. 4, 5, 6, 7. It's always hard to draw, but here are 8 horizontally stretched points. And here's the floor diagram that we looked at before. And I claim that there's precisely one tropical curve corresponding to this floor diagram, and that we can draw it through the points that we fixed up there. How are we going to do that? Well, so those points are numbered, right? 1, 2, 3, 4, 5, 6, 7, 8, and our points are also numbered because they are horizontally stretched. Okay, and then let's start with the plaque points, because the plaque points are points on elevators. So we can just draw an elevator, just a piece of an elevator locally, a piece of an elevator through those points. Keep the weights, of course. Okay, this is not yet a tropical curve. What do we do next? Well, we try to make an approach of drawing a floor. How do we do that? We start by drawing an upwards end. This upwards end will meet one of the elevators, either this left elevator. Sorry, this picture is terrible. Let me try to, it's very hard to draw those details sufficiently well. Let me try to draw a local picture first, and then trying to do that better for this picture here. Sorry. So a local picture of what is going on is I have some elevators on the left, I have some elevators on the right, and I have a point condition which I need to meet, which needs to be a point condition on the floor, right? And now I just go ahead and start my floor somewhere. Somewhere is the first elevator that I meet. Then I know by the balancing condition how I need to continue. Then I meet the next elevator. The balancing condition tells me how to continue. I meet the next elevator. Yet again, the balancing condition tells me how to continue. You can see I've drawn my elevator here a bit too long. Let me correct that picture. Okay. Okay, fine. Yet again, the balancing condition tells me how to continue. And now I've drawn a floor. And you can see, okay, the floor does not meet the point. Unfortunately, I haven't done it correctly. But what if I had started a little bit to the left with my end, trying to complete the elevator? Well, then this whole picture would just be shifted a little bit to the left, right? And now you can see I can just shift as much so that I actually meet this point here. And there's a unique way to do that. Yeah, so there's a unique way to complete the tropical curves to a floor. And admittedly, in this picture, the picture is just not big enough. It's not detailed enough to really make this precise. I can try, but it will be a little bit cheated. It'll sort of look something like this, a unique way to complete, sorry, that's this slope, to complete the tropical curve to a full tropical curve. But this is the way we go backwards, and then we have established the bijection, and then we know that we can count tropical plane curves by counting instead floor diagrams. And I want to finish by showing you how this really works. I want to compute N30, which we know is also equal to N30 algebraically, which we know is also equal to N30 floor. And that's the way to really compute this number. How do we do this? Well, first, we know there must be 3 floors. So let's start by drawing 3 floors. Then we know that, what do we know about the edges connecting the floors? They have to be connected, of course. There have to be elevator edges connecting those floors. what are the options? I could have a weight 2 edge here and a weight 1 edge here, or I could have a weight 1 edge here and a weight 1 edge here. In that case, however, there has to be another edge leaving here because of this condition about the weights of the incoming and the weights of the outgoing edges. Here, this is already settled because 2 come in and 1 leave. Here, only 1 comes in and 1 leaves. So there needs to be another edge in this direction. So what are the possibilities for this edge? What could it do? Well, first, let's continue. I mean, on the left of the floor, also something has to happen. And in this first example, there's only one thing that can happen. There have to be 3 edges leaving. There are still 3 elevator points which have to be hit. So this is the only way to complete this thing to a full floor diagram. Now this is a weight 1, so 2 edges have to leave. And now we can see that we have choices how to complete this picture because we have 3 points to meet here. And we can choose sort of who meets what point. So this guy could meet the 3rd point. Or I have to draw the other options also. Or this guy could meet the 2nd point. Or it could meet the 1st point. So these are these options. Let me just check on my notes which ones I have right now. No, there's actually more choices. We went to those missing points right away, but nobody told us that the 3 points, nobody says that the 3 Plaque points have to come first. It is also possible that there are just 2 points and then a floor. Then those 2 points have to go to the floor. They connect here. And then this guy could go here. Or it could go in between. Or it could be here, right? Okay, and the final possibility is that the floors are not connected in the way I just said, but that the floors are connected as follows. There's an edge going to the last, and there's an edge going to the second from the first. If that is the case, then there's 2 weights leaving the first floor, so there have to be the 3 edges leaving this guy also. And now I have possibilities for the orders of the elevator points here, right? So the elevator on the down point, let me mark this first. And then you sort of see 3 segments in which the elevator point on that edge could land. It could be here, right? Or it could be here. Or, and that's the final possibility, it could be that point. And now I'd like you to count how many floor diagrams counted with multiplicity do I have? What's the number I have? This one has multiplicity 4. All the others have multiplicity 1. And we have 1, 2, 3, 4, 5, 6, 7, 8 of them plus 4. That's 12. And I promised earlier that there are 12 rational cubics passing through 8 points. And now we find a purely combinatorial way to count this 12. Yeah, so this is, I think, a good end point. Let me just sum up quickly what I told you. I told you that there's a degeneration from the algebraic world to the tropical world. The tropical world is something very combinatorial. In the case of curves, we're just dealing with piecewise linear graphs, weighted piecewise linear graphs in the plane, satisfying the balancing condition. Duality is very important to understand the combinatorics on the tropical side. We set up a counting problem on the algebraic side. We have an analogous counting problem on the tropical side. We can simplify the counting problem on the tropical side even further, introducing the so-called floor diagrams. And then counting those floor diagrams is really a finite problem. You saw how I had just to go through possibilities of what possible orders of those vertices can be and so on. And then this is really something that you can solve purely combinatorially. And so we have a purely combinatorial way of computing those rather complicated numbers NDG in the algebraic world, which is something that I find beautiful. Okay, so I hope that you also like this, and I'm still available for questions, of course.
Thank you. Thank you, Professor Hanna.
Any questions?
Yeah, so I just wanted to ask that the condition of having horizontally stretched, so the point condition of being horizontally stretched doesn't sound very generic. Is it generic?
Yeah, it's still generic because I'm not restricting it very much. You see, I'm saying I want my points in a horizontal strip, but they can still be anywhere in this horizontal strip, here or there or there. So you can really prove that there are generic point conditions that are horizontally stretched. They're not on a line, right? I don't want them to be on a line.
Okay, okay. So as long as they're within the strip, it's fine.
Yeah, they just have to be, and there's a lot of freedom, right? I can move. Right. Yeah, and that freedom is sufficient somehow to show that it's possible to find generic point conditions in the strip.
And all of this works for floor decomposed tropical curves, right? So what if you do not have floor decomposed, but you don't count them eventually, or?
So there are, I only showed you one way of how tropical curves can be counted. There are also other ways how to count tropical curves, but for arbitrary point conditions, there's not an answer. Like if you really, like I sketched before, if you really give me just 8 points and ask me what are all the rational tropical cubics through those 8 points, I don't know what to do. One thing I can do is I can start from a point configuration that I'm familiar with, draw the tropical curves through them, and then sort of deform my known point configuration to the new point configuration, taking the tropical curves along. That is an algorithm that I believe has also been implemented by a student of my colleague at some point, but it's not very public in any case. So there's not a serious algorithm to compute the number of the tropical curves for an arbitrary point condition. If we really want to come up with numbers, what we usually do is to try to pick our point conditions smartly and then have a way. Sure.
So in continuation to the same question, are there isomorphism condition between the tropical curves? Because you are translating it, because the counting mean you are counting different tropical curves, right?
You mean if I have two different point conditions?
Yeah, some isomorphism condition for the tropical graph, I should say, yeah.
I see, okay. Okay, because I think I understand the question. So the tropical curves, they come from metric graphs, and we have graph isomorphisms, but they need to fix the metric, right?
Yeah.
And then if you have an embedding phi to parameterize a plane tropical curve, then the graph isomorphism also has to respect the embedding. And then there's actually no chance in this setting. There are settings, like for example, if you have a 3-valent vertex, let me just sketch a 3-valent vertex. And now this 3-valent vertex is mapped to one line, where this has weight 2 now, yeah. Then this has an isomorphism. Then this has, then you would count this as a 1/2 for this isomorphism. But such tropical curves, you can prove that they never show up if you count tropical curves through point conditions. If you do other counting problems, they may, but not here.
So this problem cannot be transferred completely to the graph theory solver, right?
Sorry?
So this problem cannot be translated into graph theory isomorphism.
Yes, it can. There's an isomorphism here, a graph theoretical, right? Exchanging the two edges are indistinguishable, so you can view this as an automorphism. So yes, the automorphisms of tropical curves are graph automorphisms, graph isomorphisms.
Okay.
All I'm saying is they don't really show up much in our counting problem.
Okay. There is another question which is a little bit diverse from this particular topic, because the subdivisions you are obtaining, it's a kind of the subdivision of the simplices. I understand this is one of the topics. So again, there is a quest of finding all possible subdivision of a simplex. So whether this technique helps to characterize all kind of subdivisions, because if we consider your initial few cases where the subdivisions were appearing, so apparently that tropical thing is give a complete characterization of all possible subdivisions. Am I
that's right.
That's right?
Yeah, that's right. All possible tropical curves give you all possible so-called regular subdivisions. Regular subdivisions are the ones that come from projecting a roof map down, so to say. And this is a subject of independent interest and independent study. And it's possible to collect all those objects in the so-called secondary fan. So the secondary fan parameterizes the cones in the secondary fans. Cones in secondary fan, they correspond to the regular subdivisions of a polytope in principle. And there are programs with which you can compute such. So there's TopCom and MTopCom. So Michael Josvik has done a lot. Josvik and his group, and there are further names to be added. Yeah, but there are ways to compute those, really.
Thank you. Thank you. Are there any other questions from the audience, from the IBA side? Yeah. Yeah. Yeah, Jorge would like to have some.
Okay. Are there some similar, or is there some similar theory for algebraic differential equations? I know it's completely different of what you are explaining, but you remember me, for instance, for differential equations with polynomial coefficients or homomorphic equations on the Riemann sphere, there are some results also related with enumerative problems. Let's say fixing the singular points, you can find how many differential equations of this kind have these singular points of regular singularities, things like this. And I was wondering, something could be done related with this area, but or something has been done, or something has think about it, or I don't know. Perhaps there is no relation at all.
Right.
You know something. I don't.
Yeah, so I think some people have studied also tropical differential equations, but I don't know much about this. So yeah, sorry, I can't give you a good answer. I can also tell you that yes, there are some things, but I'm not an expert in this direction, so I can't tell you much more. I'm sorry.
Okay, that at least you know that there is someone that has studied something related with differential equations.
Yes, yes, yes.
Professor, any other question by anyone? Okay, Professor Hannah, can you just briefly open up, just give a revision of the open problem, maybe if the projects where the students or the participant would be interested in?
Sure. Right, so there are several open problems concerning tropical curve counts. One is I'd like to point you to a series of papers by Thomas Blommer, which were put very recently on the archive. And he studies counts of tropical curves on a cylinder, so to say. So, you know, it's very hard to draw, but let me try to sketch something like this. This is now, it's only a sketch, okay? So something like this, tropical curves on a cylinder. He studies things like that, and he tries to come up. So he has some very interesting results already, but there are still questions to be solved. For example, how to count such guys using a floor diagram technique. And then there's also another open question which I can mention. So there are different counts of tropical curves, and there's also a count which fixes the combinatorial type or fixes the abstract tropical curve. Fix points and the underlying, well, it's called a skeleton of the abstract tropical curve. I'll tell you more precisely what I mean by that. So what does it mean in genus 1? This has no meaning it doesn't have any meaning in the rational world. What does it mean in genus 1? In genus 1, the abstract tropical curve will have one cycle, right? No matter how it precisely looks, it has one cycle. And what we mean by skeleton is precisely the cycle. We don't care for the ends, it's just the cycle. Now in genus 2, let me also give you a quick sketch of a tropical curve in genus 2. So there are actually different possibilities. In genus 2, it can look like this, or it could look like this, roughly. So the abstract, so I'm taking sort of the smallest subgraph that has the genus, yeah? This. And then I don't care for how many edges form the cycle, right? Here it's the length of the cycle which I care for. And here I have 3 lengths, yeah? The middle length and outside. And here I also have 3 lengths, the bridge length and 2 cycles. And I want to fix those 3 lengths and point conditions. So in genus 1, this is solved. There is a way to count such tropical curves. In genus 2, this is open. There are some very technical, complicated questions behind this, though, I have to say. So the question, which algebraic curves tropicalize to such genus 2 curves is very difficult. So, but there's still some combinatorial things to find out, maybe. Yeah.
Thank you very much. We would like to thank you once again for your time, for sparing your time, especially in the morning, for arranging these lectures. And definitely we give you, we disturb you a lot by asking silly questions, because we are very naive in this new area of tropical geometry. But I must say that you was quite supportive to all those questions. And again, we asked you multiple revisions, and you were quite accommodating all of our requests. Thank you very much, Hannah. And we would like to give an applause to you for your time and effort. And there is a souvenir. We are just showing you. We can only show you here at the moment. Okay, this souvenir will reach you very soon in upcoming days.
Thank
Okay,
you very much.
and oh, this is a special kind of souvenir, what we are going to offer to all the speakers, and we will post it. Once again, thank you very much. And this is unfortunate we could not have you here. And we hope that with this CIMPA school, there will be few young students who will pick this topic for exploring. And definitely there are lots of interesting problems which have very deep roots, not only in maths, but also in theoretical physics too, modular spaces. And that is a topic which of interest for various reasons. So once again, thank you very much, Hannah. We are getting late now. So maybe we could have one picture with you.
Sure.
Yeah. इधर से करना पड़ेगा. पता नहीं है. Yeah. इधर का क्या करना है? Oh, उधर करना. Okay. It is better now. This time we are going to be invertive in taking the picture. I request all the part. It is better ऐसे बैठे ले लो. It is better. सबकी cover हो जाएगी. Yeah, I will share this picture with you, Hannah, afterward.
Okay.
Now please look at the camera. Thank you very much. That's it.
Sure.
Thank you, Anna.
Yes.
Thank you very much.
Okay. Then I wish you a very successful summer school for the next week also.
Next week also where?
Yeah, they are wishing us success. They are wishing us.
Oh, sorry. Thank you, Hannah. Thank you.
Okay. Bye-bye.
Bye-bye. Take care. Okay. Now we are moving to thank one of our speakers who traveled all the way long from Canada, Halifax to here. And definitely she's in the, we are giving her a very tough time with a lot of burden because she's the one who is taking care of all the problem solving sessions. All the problem solving sessions. Yeah.
Gee, the participant would like to share some views. Please, Rajesh.
Okay, please go ahead.
Thanks, Madam Hannah.
She's there. No, man, chali gayi hai ke? And she has left now. Sorry, I'm sorry. I should ask. I'm sorry. Really sorry. Maybe you can share your views regarding to other speakers. Now, okay, we have Dr. Sara Faridi with us. Let me tell you that she is extremely busy lady in her university and center of too many things. You have seen her dedication during the lectures, even after the lectures in the problem solving session. She is in too many administrative things in Dalhousie University, not only Dalhousie, but also actively involved in promoting mathematics in the region, active member of the Canadian Mathematical Society, then linked with ARMS, too many paperwork, too many duties. And moreover, she was in charge of Canadian Mathematical Contest. You people might know the International Mathematical Olympiad, the arrangements of the Canadian team. She happened to be arranging too many things there, but she's equally humble. You have seen that. She is very cooperative. And now I would like to request Dr. Sara Faridi and Dr. Hassan Azad to present the souvenir to Dr. Sara. इसको open कर लो. I think this should be open too.
Thank you. Thank you so much.
It's an honor that you could come here and give
Wonderful
us your
to hear.
valuable time.
Thank you. Thank you so much.
Dr. Sarah will be leaving this coming Sunday, so probably this is the right time to give her the souvenir. But definitely this is not the end. She is going to conduct the problem solving session today, and you can see her dedication because we already have a planned visit today to visit somewhere, but she dropped that idea and she said that I came here to do this kind of stuff, to do the exercises, and try to spend as much time as I can spend with the participants. So that is so kind of you, Sarah. And I really appreciate the way you are explaining. And now almost everyone in this school has learned the linear resolutions, the free resolutions. Now, IB Karachi, you would like to say something before we missed you? IB Karachi people. Yeah.
Assalamualaikum. Thank you so much, Ms. Sarah, for coming to Pakistan to teach us this much. And seriously, I don't have any background in the subject, not that much, but you helped me a lot in solving things. Your way of teaching is very, very good, and I learned a lot. I learned the way of teaching from you also, and I've learned so many things. So thank you so much. We would like to see you again here. Also in IBA, why not? And all the best for all your lectures. Thank you.
Thank you. Thank you. That's it. Okay. Now, Professor Jurke would like to say something with all. He would like to talk about something. Sarah, you would like to say something? Okay, you would like to say it. Okay. Okay. Yeah. No.
I need 10 minutes more or less.
At 3?
10 minutes.
Yeah. Okay.
No, I would like to make the presentation of the different CIMPA activities and information. But I don't know which is the best moment. It's now, or the lunch, or is it this afternoon? Or...
You can talk to the participant right now,
Okay.
if possible. Would you like to present something?
Yes.
It is better than at 3 because there is a prayer time and then people has to go. So anyways, but there is something for you. Sahasan, I request you once again to please come forward. You came here for the first time in LUMS, and in, definitely you happen to be there in Pakistan. Yeah, we would like to present you a souvenir because Professor Khorke is a supervisor of this school, and with his kind support, we were able to manage all these arrangements, and I would really appreciate his cooperation. And there is a souvenir from our side to Professor Khorke.
ये खुलेगा कैसे?
It's impossible to open.
No. Very easy, actually.
Okay.
It's a pleasure that you could come here.
It's a pleasure for me.
Thank you so much for your support.
Thank you for everything.
Nothing to thank.
Okay. Thank you. Thank you.
Now you can have lunch. Now this because this is a Friday, so we will meet here again at 3 o'clock instead of 2:30. Okay, 3. Thank you. I need to make few announcements, and there is a presentation by Professor Khorke.